Just to check, everyone can see my screen, right?
Yeah, you're good to go.
Okay. So today we're covering intrinsic part design and a little bit of basic feature creation, like extrusions and revolutions, and then basic hole. So yeah, let's begin. Why is having a well-defined building style important? I don't know. Anyone want to answer this question? Please don't. It's rhetorical. So, as you might note, I've used a slide before, I think, in my strategic design presentation, right? 254 in particular tends to go with a pretty basic design layout every single year, right? They have tubing, they have gussets, and that's basically it, right? Tubing, gussets, plates, and that's how they run every single year. And it's gotten them 4 world championships, right? It's less important what you use, and most important that you actually have a set, defined path what you use. You can use sheet metal, you can use tubes, you can, I think 330 used like bent tubing. What really matters is that everyone in your team agrees on and knows what design solution you are going to execute and how you're going to do it beforehand, right? We went over that a bit in the strategic design presentation. So we're getting a bit deeper into that in this presentation, but first, yeah, this is a rough layout of the design standardization we've done so far. We use 1032 screws every year. Thus far, we've used socket head. Maybe in the future, we'll switch to using button heads, like 254 and 1678 do. We use 3/16 flat head rivets, and we use WCP bearings on all of our rotary contacts. In 2020, we used Teflon film on our prismatic contacts. It is yet to see whether we'll do that in the future. I hope we do. We use polycarbonate for our sponsor panels and deployed mechanisms. We use internal gussets when we can't use external gussets. 6061 tubing for most of our construction. First planetaries for most of our mechanisms. WCP dog shifting gearboxes for our drivetrain. 973 is mechanism style, 254 is drivetrain style. That's the rough layout we go for all of our standardization.
And don't worry if you don't understand what some of those mean. We will be going over those, but essentially they're the WCP dog shift and versas are like parts that we buy from outside that we use to simplify our lives. And the drivetrain style and mechanism style are just how we design those sections of the robot.
I think my computer is currently in the process of failing. Not able to do anything. I don't know. You'll want to take over?
Sure. Do you want me to present it? Sure.
Yeah, sure. Autodesk and too much for my computer, it seems.
Here, end your screen share and I'll...
Never mind. I'm good.
Oh, you get it? Nice.
Yeah. So our primary construction style is with tubing. Tubing is effectively just extrusion. You can see a few images of it back here. When we looked at 254's images, right? So the way we generally design tubing is by creating a center rectangle, spreading it out, dimensioning all of our sides. Then we offset inward by either 1/16 or 1/8. Those are the two thickness types we tend to use. We only use 1/8 if we really need to, like, have a sturdy mechanism, or if we need to put a bearing into something. In the past, we have overused 1/8 a lot. Hopefully in the future, we shift more towards using 1/16 for basic construction needs. So here's just the process you go through, just extruding everything. I like to extrude from left to right. I recommend you pick a side to extrude from. you to, when you modify the length of the part later, if you constrain one side, and that's the side you extrude, length, your assembly won't break. We'll get into more of why that happens later. We have an assembly presentation coming up for how to use assemblies in Autodesk Inventor. But I constrain all of the left sides of my tubing and do my extrusion away from the left side. That way, the assemblies don't break while I'm in the process of modifying tubing lengths. Just leaving that in there for future reference. So you can set your material in the top. You might be able to see, I'm pointing that out here. We use aluminum 6061 T6 for our tubing. So it's the alloy 6061 that's been heat treated to effectively T6 is the standardized name for it. Yeah. Then we select a side, we sketch on that side. I use construction lines because we don't actually want to do anything with the lines. They're just for the purpose of placing this point here so that we can use a hole. I selected two surface because I didn't want it to go through the other side. If you select a through hole, that hole will go through the entire piece of tubing. I just wanted to go through one side, so I selected the other surface and used the two surface termination instead. You can also use a distance termination. I prefer two surface because it allows you to modify your thickness and still maintain your holes without edit. So rectangular pattern. I believe we went over rectangular patterns for sketches in our last workshop. For this one, you can also do it with features. A brief note on features versus sketches, because for the most part, everything you can do with a feature, you can also do with a sketch. If you want to modify a sketch, it's a whole lot harder to do that and then maintain an assembly versus just modifying a rectangular pattern, which is a feature. If you can use a feature instead of a sketch, it's just much easier to modify things after you're done using them. And we will end up modifying over a season. Even if you don't think we will likely end up doing so. So if you can use a feature in any system, you could use a sketch, pick the feature over picking the sketch. So the difference in this rectangular pattern, the feature is rather than selecting a sketch element and then patterning that, you are selecting an actual feature, in this case the hole, and then you're patterning that instead, right? So we've patterned this hole across length. So it's created a simple 1-inch interval hole pattern. This is our standardized hole pattern. We use this for almost everything. It maintains a good weight as far as all of our rivets go, while also maintaining a large enough distance, a small enough distance between each hole that whatever is being mounted to that piece of tubing is still structurally sound. Now, because we do all of our, in the past we used to do our hole patterning on our Bridgeport mill. You don't need to know what that is, but the long and short of it is it's not capable of doing as complex operations as our new CNC mill. So we used to just pattern the entire thing with holes, somewhat like this, right? In the future, we hope to maybe be a bit more selective about that to maintain material strength in areas where we don't need to have holes, especially with 16th tubing, since it's already quite thin and prone to denting. Moving on, you might note that 68 uses a 1/2-inch pattern instead of a 1-inch interval pattern. Yeah, most teams do use 1-inch patterns. 254 does too. 1678 likes having added strength on all of their end effectors. So it's a pretty good example of 2x2 tubing, which is also one of the tubing types we will use. We haven't utilized it in the past as far as I know, but hopefully going forward we'll begin to use it more. Effective axle design. Now this I highlighted to teach revolutions for a second, but it's worth going into it anyway, just from a design standpoint. When we're designing axles, the most important thing to think about is backlash, right? So backlash, contrary to what the words sound like they mean, is the loss in efficiency as a result of tiny gaps between parts in an assembly, right? In a perfect world, there's no gap between your half-inch hex axle and a gear. In reality, that's not so true. Backlash is exacerbated by things like gears being able to move around on an axle from side to side. So taking whatever actions you can to reduce backlash by doing just better machining standards and whatnot is a generally just good thing to do as design goes. So here's just a standard axle being made, right? We start off with this, we extrude it outwards. This is one way of making an axle. As you might note, this was a slightly different extrude from earlier. This leaves you with no surfaces that are unaffected by extrusion modification, so I tend to avoid this. I just used it for this. So, you know, it exists. In this scenario, this means that we have 2 inches extruding this way and 2 inches extruding this way. It's nice and symmetrical, perfectly balanced. So yeah, we selected aluminum 6061. As you might note, there's nothing in this axle's design to stop anything from moving from side to side. Now, in a perfect world, we just slap a spacer on there or just tighten a collar and it's fine, right? Unfortunately, both spacers and collars aren't perfect solutions. They still allow a decent amount of wiggle room from side to side. Spacers are decisively better. Collars kind of suck at it. But the long and short of it is there's a better solution. In this case, I just slapped this in here to teach revolution. So I started with a center rectangle. We put a line through the center too. Keep in mind you can't use a construction line for this because we're going to be doing some 3D modeling with it. And then we used a revolve utility. So you just select your profile similar to how you do in an extrude. You select an axis on which to rotate it. You can select this, which we almost always want to do. We don't find ourselves in revolutions very often. Most of the time it's extrusions, but it is one of the 2 main 3D modeling utilities. So I figured it would be nice to teach it. Again, that's not exactly util for an axle either, for numerous reasons, but that's not why I stuck it in here. So back to the point at hand. If we really want to make an axle with minimal backlash, and this isn't something we've done in the past, partially because the CNC mill is somewhat new, but this is something Team 971 has done a lot. They're another top team. You don't need to know about them, but the idea is this increases efficiency in the long run. So we make all of our axles out of aluminum 7075. I know the texture is kind of terrible, but that's what our hex axles are made of. So in theory, you start with that, then you extrude from that. And what happens is basically this ½ inch that's now getting milled out into a hex, that edge over there serves as a spacer in and of itself, right? Ideally, you also have another spacer strapped around it, but tiny things like this in axle design help reduce backlash a good bit. Then you can use this. Now you're using the hex axle as a spacer. You do another one. You extend a hex from that hex. This section, by the way, would go through a bearing. So if you're wrong, you have a hex axle extending from that, presumably attaching to some sort of wheel. You have a tiny addition over here, so you can put that round through a bearing. Then you have another hex, a 3/8 hex that extends from there. You put a pulley through there. You extend it a tiny bit, just make a groove for a retaining ring, cap the groove off, and you're well and good. I'm going to highlight on this for a second. I think we've shown this a couple times now. You can use the polygon tab over here to create polygons of your choice. It defaults at 6, as it should. We use hexagons a lot more than any other just random shape. So it's here, I suppose. We don't use it that often. When we do use it, it'll be for hole patterning and for axle catting. So the more you know. You cap off the end of that groove there. In theory, this axle design helps reduce backlash by a good bit. Making it is long and tedious without a CNC lathe, but it is possible. I know 971 had a manufacturing student a while ago who just did it all manually. That was pretty neat to hear about. Here's another feature. So you can also, similarly to how in the last workshop, we use mirrors on a sketch. You can also use mirrors on features, right? So we selected the entire solid. We selected our YZ mirror plane, and we mirrored the entire solid around that plane. So now we have an entire axle. This is an axle for a flywheel, in theory, that uses a minimal amount of acetal spacers to actually support the flywheel. So here's a bit of modification I decided to include because I accidentally made it the wrong length. So the advantage of a mirror is if I had been doing this with 2 different extrusions, right, I would have to modify this length twice. Now, because I mirrored it, I can just change distance A to 3 inches instead of the previous 2 inches, and bingo, it's already longer. I didn't have to change that length at all. So this was supposed to be a model of 254's flywheel for 2020. In theory, how they would have designed it to minimize backlash. We haven't done complicated axle design in the past. Hopefully in the future we can get into that a bit. I think 971 did a calculation on how much good axle design contributes to limiting backlash. I'll link that video in the channel later, but I think it came out to something like 2% for their 2018 gearbox. It was a quite large gearbox, so tiny things like that were easier to notice. 2-3%. It's pretty large. It's the largest factor out of many of the backlash considerations they tested, including using belt versus using chain, which is pretty big. You'd expect that to have a larger effect, honestly. So, and now for this other stuff. So I'm going to be explaining how to CAD this going forward. We've already covered the 3D modeling principles we need for that. So first things first, sheet parts. I used gussets for an example. We use gussets to hold together tubing, kind of like a splint. You know, if you break your leg, which I hope no one here breaks their leg anytime soon, but you know, if you break your leg, you use a splint to make it easier to heal, right? Similarly to that, gussets hold tubing together, except tubing isn't supposed to move. Gussets keep them from moving, kind of like a splint does. In the future, we might manufacture our own gussets. A lot of teams use 1/16 7075 T6, similarly to the material we use for this axle. Also 7075 T6. 7075 aluminum is comparable in strength to low strength steels. So you can get thinner stock and still achieve a strong result. Most teams use a standard 5 or 3 inches along each tube length for their gussets. The big advantage of external gussets is they're easily repairable, they're easily replaceable, and they're easy to mass produce if you have a CNC mill or a CNC router, right? Their complexity is fairly simple, 2.5D. Basically, if you can simplify a part into 2D outline for use on, say, then that complexity is referred to as 2.5D or 2.5 dimensions. You can also, just as a note, since I use gussets as an example of sheet parts, we also make our belly pan out of sheet. I mean, hopefully we will. In the past, we made it out of fiberglass. You can also make gussets out of 3D carbon fiber inlay, nylon with carbon fiber chopped into it. So internal gussets have been tried by a number of teams. They haven't failed so far as I know. I know 3339 tried that, and 1323 also tried it out. Mark Forged Onyx, which is the material we use on our final robot, can be comparable to aluminum 6061 if done correctly, as far as stress analysis shows. So strength isn't really an issue with that. It's more of repairability. If you place a gusset inside your tubing, yeah, you don't have to deal with the gusset on the outside messing with mechanisms. You can often make connections that you couldn't make with gussets, or you'd have to use a bent. With an internal gusset, if that gusset breaks or if the tubing breaks, you now have to remove the entire that tube is built around to remove the gusset and replace it, or just to remove the tube and replace it. So it makes repairability a lot, but occasionally it's a necessity, especially if you don't use welding to make your chassis or superstructure. So we'll talk more about 3D printed parts in slide 56. So moving on, plate parts. Now the major the major difference between plate parts and sheet parts is what we tend to utilize them for. In industry, I know plate parts are generally an inch or thicker. Parts that are utilized more as a skin and tend to be 2.5D in complexity tend to be sheet parts, whereas plate parts that tend to be 2.5D. 2.5D plus means is that you have, say, counterbores or depth pocketing, which means you can't simplify the part down to a 2D image. It's a tad bit more complex than that, but it does mean that the part has suitable depth to be used for purposes like holding bearings. Now, in the future, hopefully we'll be using 1/4 inch aluminum 6061 for our parts. This is what we've done in the past. And what we haven't tried out, but hopefully we can test in coming seasons, is lightened 5/16 plating, which allows us to fully. I know 254 has used it in the past, as well as 1323, so it'll be interesting to test that out. Here's an example, actually, of one of those parts. This is from Force 2013 robot. Now, it wasn't 5/16, this was actually still 1/4. I believe they left a 16th skin back there, if you can see it. Now, the reason for that was they wanted to, on the inside of the conveyor, outline the part with Teflon so that it would be easy for, I think, frisbees in that game to kind of just slide past. And they needed a solid surface to do that, so they depth pocketed it instead of going fully through and cheesing it. So we generally use plates for things where we need to have a bearing involved. They're heavier than sheet, and they don't really offer any advantages as far as strength goes after we cheese them heavily. They are stronger than sheet, but that strength isn't really utile. The big thing when you're designing a gearbox or anything that needs to hold a bearing is decreasing natural vibrations. That's why we keep the edges at about a 1/4 inch offset. If your plate is vibrating, let's say it's made out of polycarbonate and it's bending, right? Now that means your axle inside is also bending, your bearing is theoretically shifting around, and that increases backlash exponentially. So you want to avoid having a gearbox plate that bends, and 1/4 inch plating tends to avoid that quite nicely. Moving on, billet parts. Now, I love billet parts. They're kind of awesome. They are somewhat heavier. You can deal with that by designing them a bit better, but you can only go so far. Here is just an entire table of parts by cost supplier for wheels. Now, the main advantage of billet parts is you're simplifying what would otherwise be a complex like assembly of parts into one part, which reduces complexity, it increases simplicity, it makes for easier repairability. But the big thing is they're really, really strong, like unironically. These wheels are meant to hold the weight of a 120-pound robot. So billet parts manage, and also they can get machines that you really can't get normal parts. Now it's worth noting that both plate parts and billet parts are more than 2.5D complexity, which means you can't make them on a laser cutter or a water jet, and you shouldn't be making them on a router. Most routers tend to have a badly worse tolerances on their z-axis than CNC mills. So while you can do 2.5D plus and billet parts on a CNC router, since we have a mill, I'd recommend avoiding it. We do not currently have a router, but hopefully in the future we will obtain one. So the big thing outside of FRC for billet parts is they cost a lot. Now, stock cost doesn't make up a huge amount of our cost per season, so this isn't a huge concern for us as compared to other things. But we do still want to avoid using billet parts for other reasons. They're hard to machine, which means their complexity isn't really worth it most of the time. They're hard to replace and iterate upon. If we do want to use a billet part for a final product on a robot, we haven't really done this before, like to test it out in 3D print beforehand. And that is a nice segue into our next section, 3D printed parts. So almost all of the final 3D printed parts on our robot, correction, the 3D printed parts that go on our final robot are made out of onyx, which can be printed on our Markforged printers. So in theory, onyx is just nylon containing chopped strips of carbon fiber. So it's stronger than normal nylon, not by a huge amount, but by a considerable bit, right? You can increase that strength a whole lot more, though, by using Kevlar, fiberglass, or carbon fiber to increase the strength. We tend, I think, to use carbon fiber. Is that correct, Parth? Yes? No? Maybe so.
Yeah.
In theory, when inlaid with carbon fiber, as most of the 3D printed parts on our final robot should be, they can achieve strength similar to 6061 T6 aluminum. Now, that does require good handling of your 3D printer and everything. Really nicely done settings. I think Parth has a good handle on that. For the record, Parth is our 3D printing manager, I think. So if you are interested in getting into 3D printing, ask for that. Now, we do try avoiding 3D printing parts when we can on our final robot, because 3D printed parts take a long time to manufacture. Even if you, say, brought a 3D printer to your pit at competition, if a 3D printed part broke, you're not getting that part in time for your next match. So we generally use them for low intensity applications, and when we do use them, in theory, we bring a good amount to competition as replacements, since we're not making any of those on the spot. Now, while you could also, purely theoretically, use them for low-level gear, like low-tolerance gears, again, you can just use COTS gears, and they're easier to replace and less likely to break. What a lot of teams do use Markforged for on their final bot is things like Limelight, your camera mounts, since they need to be highly customizable, and probably more importantly, pulleys. Now, pulleys don't take nearly as much wear as gears might, so Onyx is a whole lot of a better choice for that. I know almost every pulley on 254's 2019 robot was made of carbon fiber. There is a small increase in backlash, but it's really, really tiny and honestly quite worth the extra benefits. If you wanted to machine belt pulleys in-house, they have to be made of an assembly instead of just being a simple, easy-to-run print operation, which leaves you, again, with one part rather than two, and as a result, less complexity, which is great. Now, the big thing with 3D printed parts that we use in high-load applications on our robot is if we need internal pathing. For example, the 3D printed gussets I brought up earlier. Not many teams have. 1323 has tested them. 971 has done similar things. 3339, the Bumblebees from Israel, have, I think, run them on several Durobots. And in theory, they're perfectly fine, right? They can handle the strength, everything. The main issue is with internal gussets themselves. Scenarios where gussets are hard to use, or maybe just like entirely impossible to use on two connecting pieces of tube, we might use internally routed gussets instead, right? Basically large 3D printed blocks that can do the job a gusset can normally. But again, we like to avoid it, and if possible. Theoretically, it's perfectly fine. In practice, it's hard to repair, and nothing is perfect, right? I don't believe this is like official terminology or anything, but in the FRC community, parts with 3D printed levels of complexity, like internal pathing, are generally referred to as 3DP, just to stand for 3D printing. So yeah, that's about it. This is a rough guide to standardization of parts on a robot. Billet parts can be made reasonably with extrusion. You can use revolution if necessary. More of the complex things can be used, but again, we stick to extrusion for a number of reasons. Plate parts can be done almost entirely with extrusion. You don't really need many cut extrusions typically either. When you're making a hole, I think I can take you back to the hole we made at the beginning, just to explain how to make holes as features. Why did I include so many slides? Half of these weren't necessary. This is longer than I remember.
Suggest with the 60 slide presentation.
True. Okay, but you can select the option to thread and counterbore. Now, there are a number of seats you can make for a counterbore. If you wanted to say make that particular one I used in the example image, you could just use a seat counterbore. So little things like that can generally be done for 2.5D plus parts in your hole operations rather than requiring different extrusion operations. Occasionally, yeah, you will have to use a cut operation. We try to avoid using extrusion and revolutions in favor of just basic holes instead, just because, I mean, it's compacting more stuff into less space, which reduces your CAD complexity. That's generally something that we try to prioritize, not as highly as, say, version control and the ability to go back and change things easily, but highly enough that it would affect our decision to use, say, a hole pattern rather than a cut extrusion. And 3D printed parts, there's one thing I can probably include here. If you don't internal strength, if your shell is good enough, then there is a shell function that you can use, and it's pretty simple. You just click shell, and then you select your offset. It doesn't really need much explanation. I could do a demonstration, but it's basically exactly like it sounds. We tend to avoid that because you can, with the Mark Forge, automatically reduce internal density and everything. So Parts can explain more about that later if he wants to, I suppose. Yeah. Anyone else want to add their own points or anything?
I think we can go directly to stuff. Does anyone have stuff?
I'm gonna grab some apples right now. Ooh, pears. Even better. Personal opinion. Pears are better than apples. They just taste better and everything.
Alright, so Dave, end the recording with your love for pears on public record. Is my audio good?
It's vibrating a little, but not enough that we can't hear what you're saying.
It happened for me too. Oh, and it's happening for me too.
Yeah, Sid, do you have microphones in? Like, do you have headphones?
I do not have headphones, so.
That
And also, my speaker is disconnected from my microphone. And as far as I know, it's not actively canceling any audio input. So it's probably me, yeah, honestly.
In that case, I think I'll just mute Sid. He muted himself. So we will go over more specific parts later. Like Sidish went over gussets and other important things that we use in our robot, as well as 3D design tools. And please just open Inventor and play around with it. You can look up robotics related things or just make whatever you want. Just playing around with it is the best way to learn. So yeah, anyone else have anything to say? Any questions?
I'm just going to add to that. I learned CAD entirely by just playing around with it. Parth and Neil would occasionally come over and tell me I was doing something wrong, but that's about it. So, yeah, just play around with it yourself. It's probably the best help we can give you, honestly. Rather, the best help we won't be giving you, you'll be giving it to yourself. Yay.
And pretty soon, we will be hosting like project workshops where we actually work together on a CAD project. And we do not know how applicable that is over like MS Teams when like we're going to be using MS Teams either way, but it's a lot easier to do. It'll probably be a lot easier to do later. And so right now we just want to make sure everyone's caught up on CAD itself. Like how to use it, not necessarily like design aspect, but just how CAD works. Sidish, I think you can end the meeting off then, or Kaushik if you have any announcements.
I mean, I say the only note I have is like, if you have any issues where like you don't have like a laptop or something, just let us know. I'll talk to Sunny, see if we can either get one from the school, or I know that we probably have members that have like laptops that you guys can use. Like I know I have a laptop that's like on my desk that I used to use for CADing, but I'm not using it anymore because I have a new laptop. So yeah, I could like probably give that to you. Yeah, just overall, if you have any issues with Inventor setup or like with tech stuff like that, please just let us know. And as well as that, actually, I guess there's not really much else than that. I would say one thing you should try doing is, I know we had you guys do like a 2D sketch last time. This doesn't take very long, but you guys should try extruding that 2D sketch. Fun fact: if you hit the E button, it opens up the extrusion menu. That's a cool shortcut that you could try.
Also, probably one of your most used shortcuts.
Yeah. Okay.
Sidish, wait, who's the one recording?
I'm recording. About to end that.
Okay, cool.
And I think that's good.